Let's start off this video by discussing Newton's second law. And Newton's second law is going to be very, very, very important in this particular topic. We're going to spend most of this topic applying Newton's second law. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Now, I've rearranged it below in the form we typically use it in. And the form we typically use it in is that the force net is equal to the mass times the acceleration. So force net means you're summing all of the forces acting on this particular mass, and that is going to cause an acceleration. Now, force is a vector quantity, and so is acceleration. This means that we have to make use of the component method that we learned in the previous unit. So we're going to say force net in the x direction is equal to force 1 in the x plus force 2 in the x. So we're summing the forces acting on the object, and that's going to equal mass times acceleration in the x direction. So this is very similar to what we are doing with saying that r of x is equal to a of x plus b of x. So we're adding together the x components. And just like a resultant, the net is the same as the resultant. And then we would do the same thing in the y direction, for force net in the y is equal to the component of the force acting in the y direction plus the component of the other force acting in the y direction, and that's going to sum the equal mass times acceleration in the y. So this is very similar to the process to find r of x is equal to a of y plus b of y. So we're adding together our x components, but instead of just being a generic a and b, they're now going to be specifically forces. What's going to be a little bit different than what we did with the component method, and we're going to practice this a lot throughout this particular topic, is that instead of solving for force net in the x and then force net in the y, in order to find the force net in the direction that force is acting in, we're going to be writing this statement out, and we'll be solving for vector A or vector B. So you're going to see where we're going to be plugging in the equations for the trig functions rather than plugging in numbers you got from using the trig function. So we'll do lots of example problems, so don't panic yet. We are now going to discuss Newton's third law of motion. Newton's third law of motion states that if an object 1 and 2 interact, so remember an interaction means that there could be a force exerted, whether it's non-zero or has an actual value. The force exerted by object 1 on object 2 is equal in magnitude but opposite in direction to the force exerted by object 2 on object 1. Now typically when I'm doing this in an actual face-to-face classroom, what I would do at this point is I would put my hand up against the wall and put all of my weight against my hand on the wall. And instead of being in motion and falling through the wall, I simply stand there, and I'm just standing there with my weight up against the wall. And the reason that can occur is that the net force is 0. So remember, the net force is 0. That means that there's no change in motion, no acceleration, no movement. Therefore, there has to be a force counteracting the force that I am applying to the wall. Otherwise, I would go through the wall. And so the wall is pushing back with a force that's equal in magnitude but opposite in direction, so that the net force is 0 and I don't move. Now the wall doesn't push me away, I don't go through the walls, the net force is 0, because there's an equal but opposite force there. Alright, so I'm going to discuss now the normal force. The force normal is a force from a surface on an object, and it always acts perpendicular to the surface. So let's say I had a table, and I put a box on the table. So it's going to have some mass. Now because the box has mass and we're sitting on the surface of the Earth, we're going to assume all of our problems are on the surface of the Earth unless otherwise stated. That means that the weight, or the force of gravity, of the object is going to be pulling down. However, the object is not in free fall, so there has to be a force that is exerted in the opposite direction that prevents it from being in free fall. And since the object is sitting on a surface, in this case, we're going to call that the force normal. Now because the surface is horizontal, the force normal is going to be vertical. or in the positive y direction. So the force normal always acts at a 90-degree angle or normal to the surface. So in this case, since the surface is horizontal or in the x direction, the force is going to be up and down, or in this case just up, in the positive y direction. So notice here I've drawn the forces with an arrow indicating the direction the force is acting in. And this is very similar to what we did with the component method in the prior topic, where I could now draw in a y-axis and an x-axis. In this particular topic is going to be referred to as a free body diagram. And free body diagrams are going to be very important for indicating the direction of the force and therefore being able to sum forces correctly. So if I now want to sum forces, we don't have to worry about the x direction because there's no forces acting in the x. Nothing is pushing the box sideways. We can say the force normal, and the force normal acts only in the y direction, so we can just write down the force normal, minus the force due to gravity, and that's going to equal mass times acceleration in the y direction. Now the box is just sitting there, and because it's at rest, there's going to be no acceleration. So this is going to be 0. So that means the force normal minus the force of gravity is 0. Or that the force normal is equal to the force of gravity in this particular situation. So they're equal but opposite to each other. Now, before I create the misconception that the force normal and the force of gravity are always equal to each other, let's add another force to the system. Let's say I am pushing, so I'm applying a force to the top of the box. Now we have an additional force acting in the negative y direction. So now when I go to sum forces, I'm going to have the force normal minus the force of gravity minus the force applied equals mass times acceleration in the y. This is going to be 0 once again because it's not in motion. So the force normal minus the force of gravity minus that force applied to the top of the box is going to equal 0. So I can rearrange this to say the force normal now equals the force of gravity plus that force applied. So the more you push down on the box, the more the table has to push up on the box to keep it from going through the table. So the force normal is not a constant value. It depends upon what is pushing down. Now there is a limit to this. There is a point where you can put so much force downward that you actually break the table, but we're going to avoid those situations in this particular course. Now I'm going to introduce the force due to tension. The force due to tension is a force exerted along an extended object, such as a rope or a wire or a chain, on another object. And the magnitude of the force remains the same the whole way through that extended object. So let's suppose that we have our box now, but it's suspended from a rope from the ceiling. So it's still going to have mass here. So that means because it has mass, and once again we're on the surface of the earth, there's going to be a weight pulling down. But this object is not falling. It's not in free fall, so there has to be another force acting on it. And that's going to be the force due to tension from the rope. And what I mean by the magnitude of force being the same the whole way through the entire extended object, the force exerted by the rope here on the mast hanging, or box hanging, is the same in magnitude as the force experience, or the ceiling experiences from that force. What's going to be different is that the mast is held up by that particular rope, but the ceiling is being pulled down on by that particular rope. So the direction is not the same, but the magnitude of the tension is the same. Alright, so those are the only forces acting on the object in the y direction. There's no x direction forces. So we can sum our forces. The force due to tension minus the force of gravity is equal to mass times acceleration in y. Since it's not in motion, our acceleration is 0. So we can say the force due to tension minus the force due to gravity equals 0. So I can say that once again they're equal but opposite to each other. And I want to take a moment here to also remind you that the force due to gravity is equal to m times g. And for that m times g, notice I've already made this negative, So that means when you plug this in, you're going to plug in a positive 9.8 meters per second squared, because I've already handled the fact that it's negative up here. So the acceleration and the force are always going to be in the same direction.